Well, once upon a time, I dare say, Claude Chabouty organized the first journée arithmetic here in Grenoble. And I was in those days an undergraduate, and I attended the journée as a curiosity for me. And now it's a pleasure to be again here in Grenoble for a journée arithmetic 53 years later. So now we begin with the talk by Umberto Zannier, Unlikely Intersections and Pell equations in Polynomials. And I give you.
Thank you very much.
I
have this microphone. Thank you. Thank you for the introduction, and I'm very pleased and honored to be in this conference. And I am very grateful to the Scientific and Organizing Committee for the appreciated invitation. So my talk will consist essentially of two parts. In the first, and all of this is joint work with David Masser. And the first part, I shall quite briefly present some recent results with him. And in the second part, I will present an application of them to a function field variant of Pell's equation. So this joint work concerns, roughly speaking, conjectures raised by Richard Pink, around 2005. And they, very roughly speaking, they vastly generalized the Manning-Mumford conjecture on torsion points on subvarieties of abelian varieties, but extended also to other contexts like the André-Oort conjecture. I should mention that similar conjectures were raised independently by Boris Zilber. They were somewhat less general and a little bit earlier, and with entirely different motivations coming mainly from logic. And further, some very special cases were raised in a paper, in a joint paper with Bombieri and Masser in 1999. Were really very special case limited to tori rather than abelian varieties. But some of these cases were later dealt with by us and with Morin and Habegger. And the whole topic often goes under the name of unlikely intersections. So I won't describe in any detail the whole context for lack of time, if not for other reasons, but I shall try to motivate, for instance, the denomination by presenting the results with Masser. So let me introduce just a bit of notation. I shall let A be an abelian surface scheme over a curve, which I call C, and defined over the algebraic numbers. So this A is just a family of abelian varieties of dimension 2, parameterized by the curve C. Just to draw a simple picture, here we have C, and above each point lambda of C, we have a surface, an abelian surface of dimension 2, which I call A lambda. And so the total space of this is a threefold. Okay, and I shall be interested in, so you see, for every surface in the fiber, every fiber, we have torsion points. So if I fix the order n, for instance, the dimension, complex dimension is 2, and we have, so n to the 4 torsion points of order n. And when we vary the lambda, these torsion points fit to give a curve. And this curve is a torsion subscheme, so-called. So this curve may consist of several components, by no means irreducible. Anyway, now I am interested in what happens when I let n vary among all integers. And so I denote by A tors the union of all of these torsion subschemes. So it is a denumerable union of algebraic curves. And finally, I pick a curve x, just an algebraic curve inside A. And so the set, in the spirit of the Manning-Mumford conjecture, the set of interest is the intersection of x with the union of these torsion subschemes. So each point, you see each point here is in the intersection of a given curve with one of the curves in this denumerable family. And since we are in a threefold, we call it unlikely. It is an unlikely point because if we pick two curves in a threefold, we do not expect them to intersect at all, except if there are special reasons for this. So this justifies the denomination of unlikely intersections. And the theorem that I state now, it is joined with Massa, and says that this set, so it describes these unlikely intersections in finite terms, which, to be precise, means that this set is contained in the union of finitely many proper group subschemes. So we have finitely many proper group subschemes which contain all the intersections, and I shall illustrate with examples how one can draw further consequences from this. But this is somewhat a reasonable conclusion to draw. You see, when we take a proper group subschemes, the dimension goes down, so the intersections were unlikely if seen in the whole space, but they can become likely if you restrict them to the lower dimensional group. So pink, actually this is a very special case of these general conjectures of Pink. He considered semi-abelian schemes and also of arbitrary dimension, and also the variety X is not a curve but has arbitrary dimension. And you can consider unlikely intersections not only with torsion subschemes but with subschemes of higher dimension. I won't pause on this in any other sense. So let me give a couple of examples. First example is when A lambda is constant. So in this case, we have merely a special case. We fall in the two-dimensional case of the Manning-Mumford conjecture. And the same happens if the curve X is vertical, so contained in a single fiber. So this justifies the analogy with the Manning-Mumford. And the second example is due to Masser, and actually he formulated it independently of Pink and Zilber, and this motivated much of our joint work in this direction. This is a genuine example going beyond the Manning-Mumford. So Masser's example, he considered the Legendre elliptic scheme over the projective line minus 3 points. So this scheme is the usual, defined by the usual Weierstrass equation. You see, we move lambda in this space, in this curve, a fine curve, and find elliptic curves. And Masser picked 2 points, parameterized also by lambda. And for the sake of concreteness, I shall follow his original example and just pick 2 very concrete points. The first one is the point with abscissa 2, so the y coordinate is just this. I will forget about the sign, which is immaterial now. And another point q lambda, he chose the point with abscissa 3. So we have 2 points, and these points lie on the fiber L lambda. I denote by L the scheme. So now the question, I consider this set the set of complex lambdas such that both p lambda and q lambda are torsion. Set of complex numbers. The question of Masser was, is this set finite? And the answer is yes. And it follows rather soon from this statement. One has just to take A to be the square of the Legendre scheme, and we take X to be the curve described by the pair P lambda times Q lambda. Now it is quite easily checked that these points are independent, generically independent, so they don't lie, the pair doesn't lie on any proper subscheme of A. So this means that the intersection is finite with any proper subscheme, group subscheme is finite, and so there are only finitely many group subschemes to consider, and so the intersection with the whole torsion points is finite. So in this example, the scheme A is a square of an elliptic scheme. And this was the object to work out a generalization to all products of elliptic schemes, was the object of a paper, and then in a subsequent one we dealt with the case of arbitrary products. And finally we worked out the case of a simple abelian scheme of dimension 2, so it doesn't split. These cases, in fact, present some different features. They are not completely equal to treat. And also the transition, I should just say a word, of Q bar. Here we expect that the same conclusion holds by replacing the Q bar with the complex numbers, but there are issues which are more intriguing than expected in doing this, because the methods work as they stand, work only on the algebraic. So some argument is needed to draw further. So speaking of the simple, thinking of this case of a simple abelian surface, I should mention that the conjecture, so the simple case had been conjectured by Shou Zhang already in 1998, so before and independently of Zilber and Pink. Zhang was mainly interested in height issues, but as a corollary, he stated just the case of simple abelian surface of this theorem, actually in a slightly different language, which anyway I should like to state. So this is another version. And with the same notation, so we assume that A is simple. And by simple, I mean that the generic fiber is geometrically simple. So let A be simple and let sigma be a non-torsion section. Then there are only finitely many points x in the curve C such that the value of the section is torsion. So this is somewhat a strong local to global principle. So if the torsion is not, if the section is not identically torsion, then it becomes torsion only finitely many times. And again, I should like to give an example. So let me write it here to save space. An example which shall be relevant also in the application. So I let now a hyperelliptic curve u square defined by this sextic u square equal t6 t to the 6 plus t plus lambda. And now lambda is the parameter, and except for finitely many values of lambda, this is a genus 2 curve, and I consider A the family of Jacobians. So we have indeed a family of abelian surfaces. And this curve has the normalization of this curve has, for each lambda, has 2 points at infinity, which I denote infinity plus and infinity minus. Of course, they depend on lambda, but they are thought to be 2 points on this curve depending on lambda. And I take the difference. The difference of these 2 points is a divisor of degree 0 on the curve. So it defines a point in the corresponding Jacobian after we choose some embedding of the curve, for instance, with respect to one of the 2 points at infinity. And, but we don't even need that. Anyway, so it defines a section. So sigma, let me denote in very brief terms. It is the section associating to the lambda the linear equivalence class of this divisor. And it may be checked. It is non-torsion. This requires some checking, but it may be done. And also some checking is required to prove that this family is simple. Various methods are available. For instance, there is one by Stoll based on reduction modulo P. It may be checked, so the assumptions are satisfied, so we deduce that the conclusion is true. So this difference is torsion only for finitely many spatial values of lambda. I shall show an application of this later. So I should also remark that there is a theorem of Silverman about specializations and heights, and immediately this theorem of Silverman gives, special case of this, gives bounded height here for the lambdas. If also the torsion is defined over Q bar, the points such that sigma of x is torsion have bounded height by Silverman. Gives a bound for the relevant points. So the finiteness conclusion becomes immediate if we restrict a priori on to points of bounded degree. So the theorem is uninteresting, except perhaps if one allows x here to thinks of x to be to have any degree. So about the proofs, I shall also say very little. So the proof is based on the following principle. One views the fibers A lambda as complex tori. And then by means of a basis for the lattice defining the torus, one can associate, one can see the torsion points as rational points in a suitable way, of course. And now what one does is one picks one point, one torsion point on the curve, and considers the conjugates, x sigma. So these conjugates over a field of definition for everything continue to be points, torsion points in the intersections. And so now the method consists in comparing upper and lower bounds for the number of conjugates. So the number of conjugates is the degree over some field of definition. So on the one hand, this degree is large by means of results of Masser, Wüstholz, and Sinou-David. They are deep results in transcendence. Here one must be careful because one needs strong uniformity, because we jump among the fibers. When we take the conjugates, the fibers may vary also, so some uniformity is needed, but these results are available. And then for the upper bound, one counts points in a suitable transcendental variety which arises from the context. And here one has estimates which started with a paper of Bombieri and Pila for curves, and then there was a paper of Pila for surfaces, and finally there was a joint work of Pila and Wilkie for arbitrary dimension. This work also involved all minimal structures. And this provides the suitable upper bound, and comparison of bounds shows that the order of torsion must be bounded under the suitable assumptions. I should mention here that it was also important contribution of Peter Sarnak, who, first of all, raised the very question motivating the Bombieri-Pila application to transcendental curves, because their paper had mainly treated algebraic curves. So it was very important to have the idea of going in the transcendental direction. And also Sarnak actually had foreseen some principles of this method long before in the case of Torrey. So I won't say anything about the method. It has been applied also in the André Oort context by Pila, Ulmo, Yafaev, and others. And to conclude this first part, I should only mention further joint work with Daniel Bertrand and Anand Pillai. And we extended the thing to semi-abelian surfaces, and thus this completes the treatment of the pin conjecture in the case of relative dimension 2 over a curve. And the generalizations show that some care is needed, because here Bertrand found a really subtle and surprising counterexample in dealing with the extension, non-split extension of an elliptic curve by GM. So this showed that the thing also to move the context is not usually straightforward. Okay, so let me turn now to application of this. And this application, as I mentioned, concerns Pell's equation, which I shall write in this form. And of course it is universally known, especially here. And of course it was raised by Fermat, not by Pell, and it goes back to antiquity. And here I shall change the context by replacing the ring of integers by a polynomial ring, k of t. So now the polynomial d will become d will become a polynomial, and also the unknowns, I seek them in the same ring, and I suppose at once that they are non-constant, so to avoid the trivial solutions. So, and let us immediately make some assumption about D. Just so the degree of D, in order to have solutions, must be even. I will denote it by 2 times small d, positive degree. And I shall assume it is non-square. And usually square-free, mostly square-free. Although the square factors lead to problems which are far more interesting than in the classical case, where the solvability is anyway ensured. So, and the field K, also varying the field K leads to different issues. For instance, if we take K a finite field, then the theory completely parallels the classical theory as is usual. I mean, the function fields over finite fields have usually the same properties as the ring, the field of rationals. But instead, entirely new problems arise for other fields, for instance, of a characteristic 0. And I shall think normally K will be Q bar or the complex numbers. So in this context, the solvability is no longer ensured by simple conditions on D, and may be considered exceptional, contrary to what happens in the classical case. I shall try very briefly to motivate this. But first, let me also say that historically, this appeared with, at least with Abel, if not before, who studied it in 1826. So it is not as old as the classical, but rather old. And studied this problem in connection with the integration of differentials At that time, problem was to integrate in so-called finite terms algebraic differentials, where finite terms meant implicitly that the indefinite integral was obtained after a finite sequence of algebraic operations or exponentiations or inverse exponentials or logarithms. That was the main problem. So then, then it appeared in the work of many subsequent writers, Chebyshev and also others, until recently. So let me state some basic issues. The most basic, in my view, is for which polynomials d of t do solutions exist. And of course, this depends on the field, on the ground field of constants k. So I will call, with an ugly terminology but practical perhaps, I will call good such a polynomial d for which there is some solution. And then there are questions about the possible solutions, for instance, the structure of solutions. And here nothing new happens. If we have a solution AB, then all of them are obtained by, as in the case of integers, by taking powers. And then another issue which is related to the first one is effectivity. So if we are given an explicit D, for instance, with rational coefficients, can we decide whether there is a solution? And if the answer is yes, can we compute the minimal solution, for instance? This effectivity problem, it would be easy. If the minimal degree of, for instance, the x-coordinate in a solution, so the x-coordinate is a polynomial, we may look at its degree and look at the minimal degree among all solutions. So if the minimal degree would be bounded in terms as some function of d, of the degree of the discriminant, then the problem of effectivity would be very easy. It would amount, we have just to parameterize the polynomials up to that degree, and we obtain a system of algebraic equations, and there are known algorithms to decide about the solution. But the point is that this bound does not hold. Does not hold. It may be checked that even if the degree of d of t is 4, and we vary d among all these polynomials, the minimal degree of a solution is unbounded. So this shows that the effectivity algorithm is less obvious than it might be. This also led to a counterexample in model theory found by van der Dries, Carsten Schmidt, and Schoutens. And anyway, the effectivity problem is solved. It is not so obvious, but it is solved. And nowadays it may be considered standard matter. It was not so until the 60s, let us say. Let me give some simple examples. So, for instance, taking the degree of d, so for quadratic d, we have, for instance, this identity. And here Tn and Un are the Chebyshev polynomials of first and second kind. So in this quadratic case, anyway, everything boils down to this equation, at least over an algebraically closed ground field. So it is, we may consider it an interesting from some viewpoint. The quartic case, well, now, as I told, there may be solutions, and minimal solution are of unbounded degree, and also there are cases when there is no solution. Let me just give one example. So the polynomial t fourth plus 12t squared plus 8t is not good. So there are no non-trivial solutions of the corresponding Pell. And then the sextic, let me give now a family, which actually was what Masser and I investigated. We investigated the solvability in one-dimensional families of polynomials. So not for a single polynomial, it can be checked. The equation may be solvable or not. So one thing to do is to get, for instance, a family, and the case of dimension 1 is the first case to consider. So, for instance, we can consider this family, T6 plus T plus lambda. You will remind it appeared already in the example I gave before. And now we can look at this from various viewpoints. For instance, from one viewpoint, we can view lambda as a variable belonging to the ground field. So for instance, if we take the ground field K equal the algebraic closure of Q of lambda, we may ask whether there are identical solutions in algebraic functions. And over this field, the polynomial is not good. So one may show easily, I won't have time to give the argument, but it is an amusing exercise to prove that there are no identical solutions. And actually, even if we specialize at lambda equal 1, it may be shown that this is not good, and this needs some checking, as here. This may be shown and needs some checking. And on the other hand, there are values of lambda which produce solutions. For instance, lambda equals 0 is 1. And we have the following identity. So, which produces a non-trivial solution for lambda equals 0. This solution was found with continued fractions. And then let me, this is one of the contexts where this Pell equation appears. Let me mention some contexts very, very briefly. First one is continued fractions. Here we may expand, as we do in the classical case, we may expand the square root of the polynomial as a continued fraction. In which sense? Well, we take, in place of the integral part, we take the integral part now will be the polynomial which best approximates the function at infinity. And in this way, we have the continued fraction process. And of course, in the classical case, this is eventually periodic, but now it is not always eventually periodic. And Abel proved that it is periodic if and only if d of t is good. And in this case, so the continued fraction viewpoint is interesting also because I have no time to pause also on this, but of course there are the Padé approximations to the square root, and these Padé approximations often are useful in Diophantine approximation. And so there are questions. They may be useful when the height of the Padé approximations of the coefficients does not grow very fast. And now there is work here of Bombieri and Paula Cohen showing that in this case the height grows very fast when there is no solution of the Pell. So this also relates this Pell equation with these kind of issues. And the other issues when it appears are given by the problem of integration of differentials that I already mentioned. I won't pause on this. Then another context is a context of the Diophantine equation of a special type, but nevertheless relevant. Namely, this type of Diophantine equation expressing the equalities of the values of two polynomials, f and g. It is, I find it somewhat not a unnatural problem given two polynomials to ask whether the intersection of the values on a number field, for instance q, is or not infinite. So this leads to study this defines a curve, and this problem leads to study the genus 0 and genus 1 factors, components of such a curve. And this was partially done in a joint work of Avanzi and myself, but it was only under an assumption, and recently Mike Zeev and others completely classified the situation. It is very remarkable work where I think 17 people are involved, so it is also complex from the computational viewpoint, but they succeeded in classifying. And the point is that there are families and sporadic cases, and one of the families involves again a Pell equation in polynomials. And then I could also mention work by Schinzel. He studied the continued fraction of the square roots of the value set integers of a polynomial, and succeeded in relating the length of the periods with the solvability of the corresponding Pell equation. So these are some of the context where the equation appears. And another context is the context of Bieli's functions. Should like again to be very, very brief. Bieli's function or maps. So what is a Bieli map? A Bieli map is a map, a rational map on a curve, which is unbranched out of 0, 1, and infinity. These maps are quite important. They characterize their existence, for instance, characterizes algebraic curves defined over the algebraic numbers. Now, when we have a Pell equation, let us take a solution. And for this discussion, let us assume that the degree of D is fixed. So let us think of D varying but with fixed degree. So we may associate to a solution the map x square. This is a map from P1 to P1, a rational map, actually polynomial map. And it may be seen easily from the equation that this map has almost all the branching over 3 points 0, 1, and infinity, if the x has degree n, the branching here will be 4n minus 1 plus d, plus a small d. And then there are other points with total branching at most d minus 1. No, d minus 1. So, for fixed degree of capital D, you see that, and growing degree of n, you see that almost all the branching goes above the 3 points that appear in Biela's theorem. So we have not quite a Biela map, but an almost Biela map. And then we have these branching points, which may vary, but we have only d minus 1 free parameters. This is the point. And now the theory around Biela's theorem and the Riemann's existence theorem shows that, so there is a monodromy representation associated to such a map, and this is purely combinatorial, so for given degree, the monodromy varies infinitely many ways. So this theory says that if we fix the branch points, which are at most d minus 1, the free ones, if we fix the branch points and fix the monodromy, this leads only to finitely many good d of t. Up, but there is a slight thing to take into account, up to equivalence given by the following formula, that the polynomial d of t is equivalent to the polynomial d of at plus b, where a is a number different from 0. So this is an affine equivalence. It does not affect the solvability of the Pell equation, so it is harmless for our purpose. So this shows, in turn, this shows that the good equivalence classes are parameterized by d minus 1, by a denumerable union of algebraic varieties of dimension d minus 1. So these varieties are obtained just by varying the branch points. And we obtain a denumerable union because we have this degree this degree n, which may vary. So the good polynomials, if we fix the small d, if small d is fixed, we have d minus 1 as degrees of freedom, so to say. And now, how many degrees of freedom do we have for all the equivalence classes? Well, it is very easy to see that all equivalence classes, well, each class contains a representative of this shape, and here a polynomial, and here m is at most 2d minus 2. And so the equivalence classes are put rigidly by an affine transformation into this shape, and we have only these coefficients varying. So we have dimension 2d minus 2. So you see, this shows that it is unlikely for small d at least 2, it is unlikely that a random polynomial will be good, because somewhat we have the numerable union of things of dimension d minus 1 inside a space of double dimension. So let me see what this implies if we move in families. Again, the case small d equal 1 is not interesting. So in the case small d equal 2, we have a surface, we have the good polynomials, the good equivalence classes form a denumerable union of curves inside the surface. So, if we move our D in a one-dimensional family, it is indeed likely that there will be infinitely many good ones. And this may be proved. For instance, if we take this family, it is possible to prove that there are infinitely many lambdas which give a good polynomial. But by Silverman theorem, they will have bounded height, may be shown, so they are sparse but infinite. So for d equal 3, already the situation changes from this viewpoint. We have, again, a denumerable union of curves. No, a union. So for d equal 3, we have the numerable union of surfaces in a fourfold. So if we move in a pencil in a one-dimensional family, it is unlikely. And we can prove this in some cases. Actually, we can characterize the situation. And I shall not state the general theorem but only a special case for the sake of brevity. And I shall limit to the family that we have already met, t to the 6 plus t plus lambda. So the theorem states that there are only finitely many complex lambda such that the polynomial t to the 6 plus t plus lambda is good. So and lambda equals 0 is an example, as I have shown, that I have written down before. So let me show. So as I mentioned, this is a case of a more general statement. It does not suffice. There are abstractions. If we take here a one-dimensional family of polynomials of degree 6, there are two kinds of abstraction for having this finiteness. The first abstraction is the obvious one. So the Pell's equation should not have any identical solution in the variable lambda. If this happens, then we obtain solutions just by specializing. But there is a more recondite abstraction which occurs when the Jacobian of the generic curve splits. And this gives rise to infinities, although there is not identical solution. Essentially, what happens is that the splitting forces us into a previous case of a lower degree, practically. So, the connection, so how does one connect this Pell equation problem with the previous issue? Since this was well known since long ago, probably in different language since Abel, and the connection goes in this way. So let us take the hyperelliptic curve associated to this sextic, and we now take one solution of the Pell equation, And to this solution, we associate this function. So u is this rational function here on the curve. We associate this x plus y u. So this function is regular on the whole affine piece of this curve. And not only it is regular, but it has no zeros on the affine piece. Because if we multiply it by the conjugate function, which is also regular, we obtain 1. So neither of them may have a 0. So this means that the divisor of the function is entirely at infinity. And there are 2 points at infinity. And since the divisor has degree 0, the divisor of a function has degree 0, it must be of this shape, where m is a suitable integer, positive or negative. But then you see that multiplying by m sends this divisor class into a principal class. So this point viewed on the Jacobian becomes a torsion point. And then we apply the previous theorem, and it was a corollary of it that this point was torsion on the Jacobian only for finitely many lambdas. So this involves also, as I already mentioned, the verification that this curve, that this family is simple, gives rise to simple Jacobians, which is, so on this issue, it is a delicate issue somewhat. Families, so criteria were provided by Stoll using reduction mod P and the zeta function essentially, computing the zeta function of the Jacobian and showing that it does not split. Essentially, this is his method. And then there are other families provided by a number of authors. For instance, Katz, Nicholas Katz has provided families by deep methods of deep theorems of monodromy, and the other families arise from work by Kowalski, Ellenberg, and others. There are a number of methods for checking, but this is a relevant issue in the application of these theorems, that the Jacobian is simple. Okay, and now let me conclude just by saying one word about the Pell equation when the discriminant is not square-free. Of course, in the classical case, this leads to the same, this presents no novelty, but here it does. For instance, it may be shown using the joint result with Bertrand and Pillai and again Masser. We may prove that although for this family we have infinitely many lambdas for which the polynomial is good, so this is good for infinitely many lambdas. If we modify this by a square factor, this is good only for finitely many. And now apparently, you see the square factor apparently may be absorbed in the y, but this creates that the y must have 0 as a root in this case, and this is a trivial condition in the setting, and one may prove this. And now the picture enters the picture not quite the usual Jacobian, but a generalized Jacobian of an elliptic curve. So the elliptic curve is the one associated u square equal to this, and there is a generalized Jacobian which is a non-split extension of an elliptic curve by GM, and the same proof principles go through in this paper with Bertrand and Pillai and lead to the same finiteness conclusion. So I'll stop here. Thank you very much.